Hello, my name is Titus Sewell.
I'm Jackie Brandonicio.
I'm Candace Olis.
This is our formal lab report for investigating resistance forces.
The purpose of this experiment was to model the relationship between velocity of an object versus the resistance force of fluids. Our experiment required us dropping an 8.37 gram steel ball into a graduated cylinder filled with either dish soap, oil, or corn syrup. The size and weight of the ball, as well as the volume of the liquid, was not altered the entirety of the experiment.
So we hypothesized that the ball dropped in the vegetable oil would have the greatest velocity compared to when dropped in corn syrup or dish soap, and because of this, it would have a lesser viscous force.
So the concepts we used in this project was viscous force. The viscous force is basically the friction between an object and the fluid moving past it. Viscosity is just when the surface of an object drags some of the surrounding fluid with it, and this results in one layer of fluid sliding over the neighboring layer of fluid.
Secondly, drag force is when the object exerts a force on the liquid molecules in the direction of the motion, and in return, the fluid molecules exert a force back on the object opposite to the direction of motion. This is a perfect representation of Newton's third law.
Another concept, terminal velocity. This is when an object has reached a constant velocity while falling. This is because eventually the resistance forces such as drag and viscosity will equal the force of gravity, causing F net to be 0, and the ball will not accelerate and stay at a constant velocity while falling. These are the models we decided on because we're mostly dealing with force. So we have our system schema, which the system is the ball and is interacting with the liquid through contact and the earth through gravity. Here is our free body force diagram, which shows gravity and then the two resistive forces, which are drag and viscosity.
And so these are our graphs comparing oil, soap, and corn syrup, position, acceleration, and velocity versus time. As you'll notice that under position versus time, it's a linear line, which indicates that the velocity is constant and the sphere has already reached its terminal velocity.
Now that we have our data and our concepts, we want to determine whether there's viscosity, drag, or both acting on the ball. Normally, the way you would do this is you would plot an acceleration versus velocity graph, because we know that force equals mass times acceleration, so force is proportional to acceleration, but it's also viscous force is proportional to velocity, and drag is proportional to velocity squared. So when you graph this, you would get two different curves, and you could decide, depending on what they look like, whether there's viscous or drag force involved. However, due to the limitations of Tracker, we can't do this because there's only a few frames during the acceleration of the ball, so we can't plot these curves. So instead, we're going to say that water, which has an equal amount of viscosity and drag, has this density, and anything greater than that density will have primarily viscosity, so dish soap and corn syrup, while vegetable oil, which is less, will have a mix of both, so we cannot determine which will be the primary force.
As you can see, the oil had the greater velocity, but corn syrup had the least velocity. So the viscosity constant for the corn syrup was greater than that of the soap.
So we did encounter a few errors. As Titus briefly mentioned, though we were able to track the ball's motion once it reached terminal velocity, prior to that, the ball moved too quickly for Tracker to gather data, and this is because the video only captured 3 frames, which isn't enough to create an accurate graph of position, velocity, or acceleration versus time. And then secondly, we were limited somewhat by human error, and this is because Tracker, for every frame, the position of the sphere must be determined by the human eye, which can be difficult if the frame is blurry.
In conclusion, looking at our calculations and data, there is a relationship between viscosity, density, and velocity. As the density increases with a higher viscosity, the ball will fall at a slower velocity, and this is why the ball drops faster than the vegetable oil, proving our hypothesis correct.